Good morning. Welcome to Datamura Solutions, Design for Reliability, Commissioning Assets. This is our fourth in our series on digital transformation of asset management, our online learning series. Go to the next slide, please.
Bill, there we go. There we go.
Thank you, Rob. All right. Well, this morning, our focus is on design for reliability, commissioning assets. And I wanted to cover a few housekeeping items before we get started. This session is being recorded. All registrants will receive a recording link within 24 hours of the session. We are live. We are encouraging participation. We have received some questions from some of the registrants ahead of time that we will address at the conclusion of our remarks. To submit questions, please use the GoToWebinar chat panel as a question section in there. If you add those questions in, we will address those at the conclusion of our event, and we will also summarize those in writing and provide those to all registrants. Our session leaders today are Rob MacArthur, our managing partner and CEO for Datamura Solutions, and Matt View, our program manager and chief project engineer for our applications. I'd like to ask Rob MacArthur to take over from here. And Rob, the floor is yours.
Great, thank you, Bill. Good morning, everybody. Yeah, this is Rob MacArthur. I'm managing partner for Datamura, and I'll be presenting this morning a bit on speaking about the history of design for maintainability, design for reliability, and then a discussion of the process itself and the engineering content involved in that. And then we'll go maybe 20-25 minutes, and then I'll turn it over to Matt, and Matt's going to give you a demonstration of our Asset Information Hub solution, which is an example of digitization and how we can use it to support the DFR process, which is very important, obviously. And then lastly, we'll open up the floor the last 20+ minutes or so to handle question and answer and discussion. As Bill said, we've already had a few questions come in, which is great, but obviously if any more pop up as we go through the presentation, we'll talk about them then. So a little bit of background on myself. I've been in the asset management reliability space for, I guess about 30 to 35 years, depending upon how you measure it. I was formerly an engineering officer in the U.S. Navy. I was chief engineer on 3 ships and eventually retired from the reserves as a commander after doing 14 years of nuclear submarine refueling and overhauls. I spent, a few years as a senior executive. MRO Software ran their professional services division. I was a senior vice president of asset management and the marine and offshore oil and gas divisions for ABS Group. And then I've also started 5 very successful companies in the EAM reliability space, covering technology, reliability, engineering, and maintenance process improvement. So I have a pretty long pedigree here. I have a lot of experience with DFR and the original design for maintainability, and I've made a lot of mistakes, but I learned from them. So I think I have some good stuff to share with you guys. So moving on, the first slide, no design for reliability and maintainability presentation would be complete without the dumb design slide. If you go up to Google and put in design for reliability fails or design flaws, whatever, it's impressive what kind of pictures you can find. So these are just some examples, funny little examples. The lady on the right with the phone booth, I'm not so sure I believe that. I kind of look staged to me, but I think my favorite picture is in the middle here, this train track with the foundation built across it. Ironically, it looks like a relatively well-maintained railway if you look at the ballast stones and whatnot, but I'm kind of hopeful this is a Russian railway that leads into the Ukraine, and I think there's enough said on that. So moving forward into the content here, first thing I wanted to talk about was the process, the design for reliability process within the context of the supply chain cycle process. Of course, what we see across the bottom there in blue going horizontally is the traditional manufacturing supply chain cycle, with suppliers providing us goods and services and raw materials we manufacture a product, and then the outbound logistics to our customers. You can translate this to facilities as well. It's just a little bit different. We're bringing in inputs like steam and energy and services. We're operating a facility, which in turn then supports our outbound customers, be they office workers, laboratory personnel, students, whatever the case might be. The vertical axis here demonstrates the asset activity cycle, which begins with business case through design, procurement, construction, commissioning. These are the really life cycle stages we'll talk about today. And then into the operate, maintain world, and then finally decommissioning and dismantling. The ironic thing is when we think about it though, the asset life cycle may be 3, 4, 5% of the time, the duration of the asset life is actually in these precursor business case to commissioning stages. We hope that 95+% of the asset life is in the operate, maintain phase. And then lastly, decommissioning and dismantling is maybe 1, 2% of the asset life. But the ironic thing is a lot of the decisions and designs and whatnot that we perform during the business case to commissioning phase critically impacts that operating and maintaining phase. So it's a very small sliver of time in the asset life, but it's critically important. And some of the decisions we make are almost undoable if we make the wrong decisions. And I think that's part of the essence of design for reliability. If you go back in history talking about design for maintainability, which is the precursor to design for reliability, the first time I heard of it was about 30 years ago. I was at MRO Software and I was asked by Harvard University, the facilities management guys over there, to come over and talk to them about design for maintainability. And I frankly had no idea what they were talking about. I told them and they said, well, see what you can find and come talk to us. So I did some research. I found some good stuff from NASA, from the US Navy Submarine Force. It was really at the infancy of design for maintainability, but really made a lot of sense. And I was able to go over and talk to those guys. They were doing a big facilities build out for Harvard University, and I think it was helpful to them. But at that time, when we spoke about design for maintainability, it was just a fraction of what we look at now from a design for reliability perspective. What they were looking at and including in this was, of course, the design specification, but now this new concept of capacity and reliability planning input. And a good example of this, they were using RAMs and RAMs 2 capacity planning to determine, what the required throughput were on engineered systems, a cooling water system, for example, and then what size, pumps they might need, et cetera, et cetera. But also they were starting to look at, okay, what's the maximum availability we can get from this asset? So if we determine through an FMEA or a RAG that we can establish 95% availability on this cooling water pump, then we input that back to the capacity planning, and maybe if this is a cooling water system for a facility or a plant or whatever, we might say, that's sufficient. If that pump is up 95% of the time, then we can get by with that engineering design. On the other hand, if we're talking about a primary loop reactor cooling system, that is not sufficient. We're going to need redundancy. We're going to need fail-safe engineering system, because 95% uptime on that reactor cooling system is not appropriate. And so we need to build in redundancy into the design. And these aspects were starting to come into play. But probably the biggest thing was accessibility. This is what a lot of people thought about when they thought about design for maintainability, that maintenance personnel and operators could actually get to the equipment to safely operate it, to safely maintain it, etc. I have a couple examples from my own life in that realm. When I was on the USS Wasp, which was LHD-1, I was an engineering officer. She's an amphibious assault carrier in the Navy. First ship of the class, beautiful ship, but the first ship of the class has all the design flaws baked into it. And from an accessibility perspective, just 2 examples. We ran 2 main engines, steam driven, very large shaft horsepower, 45,000 shaft horsepower on 2 shafts. Of course, 2 boilers, 2 main engines. These main engines were massive, and and they turned those screws, but of course they had to go through a reduction gear to reduce that velocity down. Those main reduction gears were probably the size of about maybe 3 or 4 F-350 trucks put together. They were very large. They had a sump of about 500 gallons of oil, which of course was critically important to the reduction gear. It might have been the most important piece of equipment or 2 pieces of equipment on the entire ship. The problem is we had an attached lube oil pump. The reduction gear could run without the lube oil pump, but you didn't want to do that too long because it maintained pressure, lube oil pressure. The problem was these lube oil pumps and their motors were outboard and installed directly almost up against the outside bulkhead of the ship. So as a result, when we went to grease the bearings on that, there was only about 6 inches of clearance between the bulkhead and the bearings. You couldn't actually get the grease gun in there. And so we had no way to effectively lubricate these. Now, one of my senior chiefs came up with a workaround. We got some surgical tubing stuff from the aviation guys, and we figured out a way to make it work, at least as we got through our first deployment. But clearly, obviously, a big design flaw from a maintainability perspective. Another example was solid state frequency converters. These are frequency converters that converted 60 hertz power to 300 hertz power for the weapon systems and communications and obviously critical systems. We had 2 buses, forward and aft bus for electrical distribution on the ship, and each one of them had 3 solid state frequency converters, which were all in one switchboard together. You only needed 1 per bus to operate the weapons suite, so we had plenty of redundancy. We had 1 PM on those solid state frequency converters, and that was to go in once a year and shut them down and basically go in with a vacuum and vacuum out the dust, which was important because if we let dust build up in there, we could have had an arc flash incident, which of course we didn't want to have. The problem is these switchboards were installed with about 8 to 10 inches clearance from the forward bulkhead and the frequency converter room. So somehow or another, we had to get an electrician back there, a couple electricians into that tiny little space, undo the access panels and actually access those. Thankfully, I had one very limber electrician. I remember his name well. And he was a black belt in karate, and he could actually get in there. But I was always panicked that he was going to have a panic attack in there or something. So I'd have a corpsman down and 2 chiefs to make sure he was okay as he did those PMs. And you look at those things, and the subsequent LHD ships, those design flaws were corrected. They did have to come back and correct those on the WASP, which of course cost a lot of money from a ship-alt perspective, but just examples of accessibility and how that can come back to bite us. And in that case, with the WASP, cause a lot of downstream costs that we didn't necessarily plan for. The little depiction you see up on the upper right-hand side of this slide is just an example of what we're talking about here, how these decisions that we make early in the life cycle, as far up towards design and procurement and installation, the cost to correct those is minimal compared to when we discover those issues, like, for example, the lube oil pumps and solid state frequency converters that we find during the operational life of the asset. And, frankly, those couldn't be corrected on the WASP until she came back into a major availability about 3 or 4 years later. So it caused a lot of operational fatigue as we went as well. So, moving forward into design for reliability, this is all built on the basis of that 30-plus-year-old design for maintainability. But now what we include is more robustness in the other asset activity life cycles. So for example, in addition to all the things we did for design for maintainability, we're now including purchasing specification. We're including the construction and installation procedure. And lastly, the final step in the process, including the commissioning and qualification procedure. So building out the robustness of that design stage and all these steps prior to the activation of the asset. So what I'm going to do now is talk about, some real life engineering component pieces, and these are good takeaways for you guys. And I would you'll get this video back, but I would encourage you, to jot these things down, because some of these are really good learnings, and these are all engineering elements that factor into these stages of the asset life that can make a significant difference on the performance and the life of those assets in their operate maintain phase. Here's an example of a purchasing specification and a little bitty thing called a balance specification. Balance specification obviously is relevant and germane to rotating pieces of equipment. If we do not specify a balance specification to the OEM, what you're going to get back is an ISO G6.3 balance on the asset, which is not bad. It's not bad. However, if we do specify a higher order balance specification, and what we recommend is an ISO G1.0 balance specification, we can reduce the vibration on that rotating equipment by 15 to 20% and thereby greatly extend the asset life. It's a little thing. We include it in the purchasing spec. It costs $0. You know, the difference between 6.3 and 1.0 for a balance technician on the wheel is maybe 5 to 15 minutes. For the 400-pound rotor that you see an example here, we're talking tenths of a gram of material that has to be shaved off to achieve G1.0 versus 6.3. But of course, the resultant impact on the asset life is about a 30% increase in the asset life, which you see depicted below, just by including that one line item in the purchasing spec. Moving over to construction and installation procedures, and I'll show you some examples of these here in a second. You know, ensuring that we have a construction and installation procedure, ensuring that we specify machine key lengths that cut to precise lengths, ensuring that we measure and ensure zero pipe or conduit strain at equipment install, which if we don't do, we'll immediately pull the equipment out of alignment when we bolt up. A precision alignment installation specification, and lastly, drill and tapping for puller rods on fit couplings and really pretty much all equipment, so that if we do find ourselves in the situation where we have to rig out a piece of equipment, those puller rod taps are already in place for us to utilize. Now, some examples of those things I was just talking about. Here you see some real life examples of some motors. The one on the far left-hand side, you notice difference between that and the one in the middle is the one on the left-hand side does not have horizontal adjusters installed. The one in the middle does have horizontal adjusters installed that have been specified in the installation specification. Little thing, not very costly at all, but it allows the millwrights and mechanics, either it be the construction crew or our own personnel, to achieve a precision alignment using jack bolts with those horizontal adjusters. If we don't have those, there's no way that piece of equipment is going to go into precision alignment, which will dramatically improve the life of the asset. What you see on the far right-hand side is one of those horizontal adjusters with a jack bolt installed. The reason you don't see the jack bolts on the other ones is most people, from a safety perspective, pull them out after they use them. But what the millwrights will use those jack bolts for is to fine-tune the alignment of that motor or whatever rotating piece of equipment they're working on as they do their laser alignment. We can also use those horizontal adjusters and jack bolts over the life of the asset as we're measuring vibration to fine-tune that alignment without having to break the coupling, without having to do a whole nother laser alignment. And it's a really effective tool and a little tiny piece that can go into an installation procedure that can pay big dividends for us. Shaft keys, I mentioned that a little bit earlier. What you see an example here on the right-hand side is a brand new motor that's getting ready to go in. And notice there's a full-length shaft key that's inserted in the keyway. That's the way most rotating equipment comes, is that shaft key will be taped to the shaft and it will be the full length of the shaft key. However, if we install it like that, which is probably what you'll see 70 to 80% of the time, because there is no procedure and the millwrights and mechanics don't know they're supposed to cut that shaft key. What you see on the left-hand side is a properly measured and cut shaft key. It looks to be just about right. I can't quite tell unless I were able to look inside that coupling, but it looks just about right. And what you notice there is, you know, when you think about a shaft key, it's sticking up out, you know, off the peripheral of the shaft, and it's a hunk of metal that's out there that's spinning as that shaft spins. And of course, with that centrifugal force and that extra mass on the outside of the shaft, we're going to cause vibration. by cutting the shaft key, what we're basically doing is leaving enough milled out metal on the shaft in the keyway that compensates for the extra amount of shaft key metal that's sticking up. Another thing we want to see in the installation procedures on the other side of this coupling is the shaft key on that side, again, is measured and cut to make up for that excess material, but it also is superimposed 180 degrees. So it's on the bottom of the shaft versus the top here, at least when the coupling goes together, so that the two shaft keys are balancing each other out as well. Both of those little tricks, put them in your installation procedure, make sure they're adhered to by your own personnel or contractors. 20% reduction of vibration, again, right there, which, you know, doubles the life of those seals and those bearings. Here we have an example of lock rings and spherical double roll bearings and some of the things that can go wrong with those. What you see on the left-hand side is the open and exposed double roll spherical bearing, pillow block bearing effectively. The little red arrow is pointing to what's called a lock ring. And when we get the bearings and pull them out of the box, there'll be two lock rings. And sometimes you install both lock rings, which will fix and hold the bearing on the shaft. On the other hand, sometimes what we want to do is only want to install one of the lock rings, which allows that bearing to float or to effectively compensate for thermal growth on a shaft. That's what you see in the middle there, which is the problem. There was no installation procedure. The mechanics and millwrights went in. This is a large agribusiness mill in the Midwest. This is a combustion oven fan. They installed both of those bearings in a held condition, meaning they installed both lock rings. Now that shaft gets to about 200 degrees Fahrenheit. The ambient temperature in that mill is about 90 degrees. The centerline length between the two bearings is roughly about 2 feet. So if you do the math, as that shaft spins and comes up to temperature, you're going to get 20, 25 1/1000ths of an inch thermal growth on the shaft. And of course, without that bearing in a floating condition, it's going to damage those bearings. And what you see happen here is they came up, they installed these bearings, they brought the furnace up, and it lasted a couple days before, bang, you can see it destroyed this forward bearing. You can see it pushed the cage right out of the bearing, and of course the bearing seized. And subsequently, when they went to replace this bearing, they evaluated the second bearing, and it also damaged and destroyed that bearing. So a very costly thing that could have been really mitigated just by doing and creating and using a proper installation procedure. Last picture here on the right-hand side is the inner ring of, again, a double row spherical bearing. This was heat and beaded onto the shaft. So what I mean by that is they got the bearing on okay during installation, but as they were loading the coupling, you know, they didn't check the shaft for burrs. They weren't checking for fits and tolerances. They got the coupling stuck on the shaft. So of course, what does any proper construction crew do? They get a torch out, they heat that coupling so it starts to expand, and they take a 4x4 with a sledgehammer and start beating that coupling up onto the shaft. Of course, as they beat that coupling in the shaft, what they're effectively doing is beating that bearing. So they started up this piece of equipment. They say they could hear the bearing clinking. Of course, they had to pull everything down, pull that bearing, open it up, and they had to replace it, but they cut it open afterwards, and you can see what happened here where the rolling elements were actually beaten into the inner race of that bearing and, of course, destroyed the bearing, all of which could have been avoided with a proper installation procedure. Shimming, two examples here on the left-hand side. You see a piece of equipment. Good news is there's a horizontal adjuster there. Second good news is, you know, when they tried to do their vertical alignment, they did shim this softfoot here, which is great, but they used a total of 13 shims here. And what they've effectively done is created a spring, and they didn't correct the softfoot. They actually made it worse. The proper procedure here would be to do the vertical alignment, get it. 13 shims is okay. However, when they finished the job, they should have consolidated shims, no more than 3 or 4 shims on a foot, to preclude a softfoot from being created. On the right-hand side here, here's a mineral operations plant. This is a pillow block bearing that drives a fan. Each one of these plants has about 40 of these fans, and they're critical to operations. They were running these fans. These fans should be running for 8 to 10 years, these bearings, without failure. They were overheating and failing after about 6 months, overheating by 40 to 50 degrees. They asked us to come have a look. And what the problem is if you notice, if you look at the right and left-hand sides of the bearing housing, you can see that they were shimmed. These were put in during construction. However, if you notice that little black gap in the middle, that's a gap where there's no shim under the bearing. And the problem is even though the manufacturers of the bearings, they'll mill out grooves on the top of the bearing housing to stop it from flexing. But with that little gap in the middle under the bearing, you're going to get a minute little bit of flexing of that bearing, which pinches the top of the bearing. And as a result, starts to build up the heat, which breaks down our lubricants. And hence, we're starting to get 6 months mean time between failure on these bearings and having a tremendous operational impact. The solution here, they went in, they pulled those bearings, they put in full face shims underneath, had to realign, but it immediately knocked out the problem. Those fans are still running today, and that was over 4 or 5 years ago. Next step of the design for reliability process, and I won't spend a lot of time on this, but this is just, again, the commissioning process and the commission and qualification procedure. This is a standard process flow for this, but what I want to make the point of is this commissioning and qualification procedure is the last line of defense, if you will. This is the last place to look and say, did we do everything we needed to do? Did we do the best job? Did we have the best purchasing spec? Was it installed correctly, et cetera, to make sure before we activate and take ownership of that piece of equipment that we've done everything we could in those previous life cycle stages to really enhance the life cycle of that asset as it moves into operate and maintain phases. So having said that, obviously design for reliability is a great thing to do. A lot of people are doing it. Or trying to do it, not only on new greenfield developments, but also using the process as they do upgrades or overhauls or replacements of existing assets. But it is a complicated process, and that's where digitization comes into play. The first part of the complication is along the upper axis here, and I've just listed out off the top of my head some of the different disciplines and multifunctionality groups that can participate in design for reliability. They may not participate in all the stages, but they participate in at least one or two. Some participate in all. But of course, we get the situation where we have to create an environment for that collaboration. We have to manage those groups. We have to make sure they're involved. We have to make sure they have a vested interest in this. And of course, that's work to coordinate and make that work across a multitude of different organizational groups. And then as we come down the process itself, from business case design all the way through commissioning and qualification, starting to think about all the stages here that may or may not be pertinent, but also all the related data flows that are occurring as we go through this process. The business case, the requirement spec, functional spec, design spec, engineering drawings, procurement spec, permitting, spare parts lists, warranty information, maintenance procedures, operating procedures, OEM technical documentation, maybe safety plan, equipment monitoring plan and diagnostics and analytics now, lockout, tagout, OEM training, installation procedure, and then of course, ultimately, culminating in the commissioning specification. And these won't all be pertinent to every asset, but we have to ask ourselves the question, is it pertinent? Do we have to do something there? And arguably there are pieces here that if I had to go back and redraw this slide, that I would add again. For example, maybe including the CMMS setup, the asset performance management system setup, the failure modes effects analysis was accomplished, etc. But the point I want to make here is to do this and do this well, you need to have a structure and a strategy for the organizational element to make sure that everybody's involved that needs to be involved. And then secondly, that we have a disciplined, standardized procedure that we follow as company X, Y, Z. This is how we do design for reliability. We go through, we check the box. All of the steps may not be pertinent to a specific asset, but we have to ask ourselves a question. Do we need warranty information on this? Do we need critical spare parts list on this equipment? If the answer is no, and we ask ourselves the question, that's okay. But we need to make sure that we don't leave any stones unturned at the end of this process, or the results won't be what we had hoped for. So transitioning over to the Asset Information Hub, what this level of digitization does for us is three things. One is it serves as a central repository to bring in all this asset information. All the things that I just described on that previous slide could live in 6 or 7 different native systems: the CMMS system, the purchasing system, the safety system, the engineering drawing system, etc. But the Asset Hub provides one central repository where it pulls information from those systems of record into one place where we can see it, and we don't have to be running helter-skelter between various different legacy systems. Number two, it provides a platform for collaborative multidisciplinary involvement in the entire process. Purchasing can go in there and see everything. Engineering can go in there and see everything. Everybody's playing on the same playing field and has all the relevant information right in front of them in one place. And then lastly, we can use it to enforce process compliance. We can enforce standards such that, for example, you can't get to the installation procedure until you've accurately and effectively completed the purchasing specification. And we can put in that kind of logic to make sure that people don't go ahead of themselves and get to stages of the process where they shouldn't be, and since they haven't completed previous stages of the process, and jump over and try to bake a cake without using any eggs, so to speak. So at this point, I'm gonna shift over and let Matt grab the presentation, and he is going to give you a view of the Asset Information Hub. Matt, you should have it.
Thanks, Rob. So just a brief introduction of myself. I'm a program manager and chief engineer for Datamura Solutions. I've been working about 4 years now, putting in these digitization solutions in place and helping create this central information hub that Rob was talking about. So I'll give a brief overview here. As you can see, the whole idea of this is just, like Rob said, to bring all of that information that he was talking about, all of the purchasing specs, all of the operations information, all of the maintenance information, into a single portal where anybody who needs to can get to it whenever they need it. Part of that's from the design perspective of what are our purchasing specs? Can we come into this documentation section, get to the documentation, and can we find all of the submittals we've done in the past? Do we have our alignment specification? Do we have our commissioning report template that we need to do for XYZ asset class? And it allows all of that information to be stored here in one spot where somebody who doesn't have Rob's 35-year degree pedigree can come in here and find what they do need to do to get to a true reliable state in their plant. Additionally, it builds out an asset registry where you have a list of all of your assets here that you would ever need, with all of the information for that specific asset linked out. So I'll just go to a quick example here. I'll just grab a tank with all of the child assets, its spare parts list, what valves go to it, what they isolate, so on and so forth, a listing of what the criticality of that asset is, and does it warrant all of the bells and whistles or not. And like Rob said, part of this can be enforced through this portal if need be, through process flows and approvals, and making sure that notifications get kicked off automatically to the right groups, such that we're not skipping steps, and we're making sure that maintenance is involved in the review of the design plan, such that we're not building it in a way that they can't get in there to do the PMs they're supposed to do. But most importantly, it's all in one spot, so everybody can see it whenever they need to see it. And like Rob said, we are bringing in as much information as we can from all of the disparate systems. So we've got a safety assessment here where you can come in here and see what safety has said about it. We've got a list of all of the work orders coming in from the CMMS so that you can see what it was. We've got the criticality ranking, so you can see how the operations team thought that this asset affected the overall performance of the plant. We've got all of the OEM documentation, so you can come in here, you can get at what was the commissioning report for this asset. Do we have a user's manual? Do we have a warranty? Do we have XYZ thing that we're supposed to have about this asset? And can we reference it whenever we need to? Do we have the engineering drawings? Can we get to these whenever we need to? And do we have performance monitoring on this? Can I come in here and see how is it performing over time? Can I change and see all of that in one spot? So obviously there's a lot of information in here, but it goes back to the point that Rob was trying to make, that yes, there are a lot of fingers in the pie for this whole design for reliability concept, and you have to have participation from all of those groups to make it effective. And this is a way that facilitates that, makes it easy for maintenance, safety, your reliability engineering group, whomever needs to be here doing it. It makes it easy for them to come in here and see what they need to see to get their jobs done and continue the operation of the asset to its most effective state. So at this point, I'll open the floor up for questions.
Why don't, Matt, I'll jump in here, reopening the presentation for you guys, but we're gonna open it up to questions here in a second. We did have 4 questions come in ahead of the webinar, so we'll hit those first and then let you guys go with any other questions. If you wanna type in any questions you have into the chat box, Bill will be able to see them, and then we'll pick those up as we go. So the first question, which came in from a dear old friend of mine who I recognize his name, says, our commissioning is done outside our maintenance organization systems. How have you leveraged external commissioning data? And I think, you know, the clear answer to that is what you were just seeing that Matt was presenting. All of that data that you see there is coming in from multiple different systems, 6 or 7 in the case of that customer. It's coming in from the maintenance systems, the engineering drawing systems, the finance system, building management system, process controls. So, you know, that is the central value of the hub, is that it allows us to pull that data into a data lake and present it real time. And the system of record continues to be those, whatever those systems are. If you're running Maximo or SAP, and you know, that still holds and owns the asset record and everything else. It's just that the hub is querying and pulling that information into one central repository and then fusing it together with data from other systems. And so that's really the power of the system, and it doesn't all have to come from one specific system. The second question I had was, it just says APM and EAM. But I think this is a good question. If I went back to that process slide that I previously had shown you, I think one of the things I would have added to it is CMMS. You know, clearly we need to make sure that as we start to bring the equipment on board, that we're setting up all the required data in the CMMS system, a lot of which is other steps of the process that you saw there. But, you know, making sure that the record is set up, it's accurate, it's correct, the PMs are set up, any predictive maintenance, etc. APM is asset performance management. This is systems like Aspen Tech and whatnot that, you know, specialize on asset condition, real-time condition monitoring and analytics. You know, obviously a developing field that's really exciting, but you know, we need to think about that up front. We might need to even think about that in the purchasing stage. If you think about, you know, things like Gould now has developed their smart pump that comes pre-wired with all the sensors and, you know, the ability to pull that data into an analytics package like Aspen. We need to be thinking about that up front. Maybe that's something we want to specify in our purchasing spec. Clearly, when we do our installation, we need to make sure that those sensors are hooked up and they're feeding whatever the system of record is going to be. And we need to be thinking about how we're going to be using those analytics. So, you know, the condition monitoring and analytics field has just exploded, again, in a really exciting way, but it's got to be included in our thoughts from a design through procurement, installation, and commissioning process perspective. The third question I have is aging facility reliability engineering approach. This is maybe a little bit outside the realm of design for reliability, in my opinion. You know, when we talk about an aging facility and how do we deal with reliability there versus a new greenfield or even just a newer plant, it's different. I would say, you know, really the thought process from a reliability perspective on a very old plant is risk management, is understanding where your risk lies in the asset base. What are your critical pieces of equipment? What are the age of them? Performing an obsolescence study that you can do yourself, or you can use other, you know, engineers or whatever the case might be to look at these pieces of equipment, look at the failure history on them, determine how much longer you have with them, what you need to do if it were a situation that you need to retrofit or remedy something, and then put together a plan accordingly. You know, all based upon what your organization's expectations are for that plant. If your company says, hey, we want to run this thing into the ground for the next 5 years and then we're done with it, okay, we got to get 5 years at least planned obsolescence on those critical equipments. If the plan is to upgrade and continue to operate that plant, well, that's a different business case. If we do get into the situation of upgrading and replacing equipment, that of course brings us right back to design for reliability. Design for reliability is pertinent not just to greenfield construction, but also we should be using this same process when we go out there and purchase and replace a piece of equipment, a compressor, agitator, pump, motor, whatever. You know, we should be using the same process. It might be a bit more slimmed down, but we should be still following that rigorous standardized process for capital replacements. And then the fourth question is, should all critical components be purchased and stored in MRO before a new machine is started and ran on site? That's a kind of yes or no question. We definitely want to do a critical spares assessment and determine what critical spares we need for this equipment, or what are the critical spares for this equipment. And then we need to make a risk-based decision based upon what we think are the highest potential failure modes. So we may determine that, hey, there are 10 critical spares on this piece of equipment, but 8 of them are probably never going to fail. Or if they are going to fail, we can get them very quickly. We don't need to buy and purchase and keep those spares on the shelf. On the other hand, these other 2 are pretty high potential failures, and there'd be a long lead in getting them. They're worth the investment to buy those and go ahead and stock them in our storeroom. Because the thing you got to keep in mind is, you know, and I was an engineer, and you know, in the Navy, so I could never have enough spare parts. But in reality, particularly in the commercial world, when we think about MRO spares in a storeroom, think about that as money sitting there on the shelf. All of the money that we spend on capital spares, you know, number one, our organizations have to spend money to get those. Normally, the weighted average cost of capital is 9, 10, 11, 12% in the US when you factor in debt and equity. Also, it costs money to maintain that storeroom, to heat it, to light it, to have storeroom attendants, etc. So your carrying cost is going to be 15 to 20% on every part you put in there. And that's year after year after year. So it becomes a not insignificant amount of money that we're putting into that storeroom. And we just want to be meaningful about it. We don't want to put stuff in there, high value items that we never utilize, because we're basically taking capital away from the rest of the business that could be used to build another plant or do another run of product or whatever the case might be. So the answer is, you want to be thoughtful about the critical spares. Yes, if it's a critical risk, you want to stock it and make sure it's in place. However, if it is a critical spare, but you don't think you're going to need it, or you know that you can get it very quickly, you may make the decision not to carry the part. Now, I would recommend, if you don't carry it though, you still put it in as a non-stock item in your MRO inventory, so that you know what the part number is, who you could buy it from, and so if you did need to buy it, you could buy it very quickly and get it. So those are our 4 preliminary questions. Bill, have there been any other questions that have popped up?
Yes, Rob, I'm glad, I'm glad you asked. I got at least 2 more questions, and I will I'll read those out to both you and Matt, and I'll ask the question twice just to make sure you got it. Okay, number 1, what's your process for associating data with assets? Is it a manual process or ... question mark? And I'll ask it again. What's your process for associating data with assets? Is it a manual process or another answer?
It's really not our process, I would say. You know, the asset information hub is configurable to marry up to a customer's DFR process, and that's the thing that I would recommend. Each person's DFR process is going to be different. You come from different industries, different organizations. Some are in highly regulated industries, some are not. So you know, it's really the customer's process for compiling that data by following that asset activity lifecycle process, but what pieces you need and what pieces are not relevant to you. The hub can be configured to match up to that very easily, and it's just that maybe some areas of the hub are not pertinent, other areas are pertinent, but really it's the customer that owns that process. And you know, we spend time with our customers ahead of time talking through that. And I know some of you folks on the call today have very robust DFR processes. Not a lot of people have the systems infrastructure that the hub provides, but a lot of people have, you know, downright pretty good DFR processes, and there's no reason to redo the wheel there if it works for you. Matt?
Absolutely, and just to tag on a little bit there, of there are cases, absolutely, depending on how well the systems of record that we're talking to are set up. If they're already set up really well and they have references out and it's set up in a relational kind of way, we can usually pull that information in within a matter of hours. There are other cases where the system of records have been neglected a little bit, and we kind of got to go in and do some down and dirty work of saying, sitting with the SMEs for that group and saying, okay, here, this is actually this asset, and it means this. So that there can be a manual part to it at times, but that's the down and dirty work that has to get done to really leverage the system. What other questions did we have out there, Bill?
Thanks, Matt. Okay, I think this looks like this might be number 6 and final. It's very direct. Who builds the system? Would you like to start with that, Matt? Who builds the system?
Sure. So the answer is it depends. So the system that I was showing off itself, the actual front end system, would be built by Datamura, but the inputs to it, that's all coming from your existing systems of record. So we'll help you make the correlations, but a lot of it depends on your business drivers and what systems you already have out there that you want to talk to and pull into the information hub. So it's a joint effort.
So if you think of the solution as being 3 layers, the front end interface that you saw, and that's very configurable. So that's a Datamura solution or product, if you will, but it is very configurable. So to your process and your needs and whatnot. Underlying that is a correlation database that sits on a data lake. That again is a Datamura product, and it's all developed and designed for asset information correlation very quickly. And then the third layer is really the integration of all the legacy systems, be it Maximo, SAP, OSI Pi, you name it. We have integrated to dozens of systems. Those integrations and APIs are open and prepared, and they're built on different kinds of systems that we see a lot, like, for example, CMMS systems, like example, process control and building management systems. So they're built to hook into those systems. Now, each one of you, of course, is going to have a different cornucopia of systems. Some of you run SAP or Maximo or Infor for EAM systems. Some of you run OSI Pi. Some of you run Rockwell. There's all this menagerie of different systems out there, but the correlation database and the APIs are built by system category and are built to plug into those systems very rapidly. So that's where each one of you would have really a custom solution, but it's the plumbing that's custom. It's not the framework of the house, so to speak.
Great. Thank you, Matt. Thank you, Rob. I think that unless we get anything else in the next few seconds, I think that's going to wrap up our Q&A. We can move to the final slide for today. Well, on behalf of Datamura Solutions, I'd like to say thank you for attending today. The session is over, but the engagement does not need to be. If something comes up in terms of questions on the content, questions on the process, data considerations, please feel free to reach out to us at info@datamura.com. Both Matt and Rob will be available for follow-up questions if anything comes up. As we noted at the top of the session, a recording will be sent out. If others in your organization do see that and they would like to engage with Rob and Matt on specific things, I'll be more than happy to relay that information and get that those questions answered and back to you. As mentioned, this is the fourth in our digitalization of asset management the series, and we're back up in May with predictive and prescriptive program considerations that will have a discussion and demonstration similar to what we did today. We do have some other industry information coming out. You can take a look at our website, datamura.com. We post those updates, those newsworthy updates on LinkedIn as well, Datamura Solutions. If there's any follow-up you need, any questions specific to how we did this, specific for Rob or Matt, again, please reach out to us at info@datamura.com. At this point, I'd like to say thank you for attending, and we'll see you in May. And thanks to our presentation team, and thanks for all the attendees today. Bye-bye.